NASA is moving steadily toward Artemis II, the mission that will send 4 astronauts around the moon for the first time in more than 50 years. The launch window is approaching, hardware is being tested, and crews are training for a flight that represents the next major step in returning humans to deep space. But as preparations continue, one technical issue remains at the center of a quiet debate. It does not involve the rocket's power or the mission's destination. It involves what happens at the very end, when the spacecraft returns to Earth at extreme speed and must survive the most intense phase of the journey. The question is not whether Artemis II will launch. The question is whether every system has truly been validated under real conditions. So let's take a closer look. If you value clear, structured explanations of complex space missions without hype or speculation, consider liking the video and subscribing. It helps support in-depth coverage that focuses on understanding rather than headlines. Artemis II is currently scheduled as NASA's first crewed mission of the Artemis program. The flight will carry 4 astronauts: Reed Wiseman, Victor Glover, Christina Koch, and Jeremy Hansen, on a journey around the moon and back. Unlike Artemis I, which flew without a crew in 2022, Artemis II will place humans aboard the Orion spacecraft for a lunar flyby mission lasting roughly 10 days. The mission will launch on top of NASA's Space Launch System, or SLS, a heavy-lift rocket designed to send large payloads beyond low Earth orbit. After launch, Orion will first enter Earth orbit, then perform a maneuver known as translunar injection, which sends the spacecraft toward the moon. The crew will travel around the moon on a free return trajectory, meaning lunar gravity will naturally guide them back toward Earth without requiring a major engine burn for the return. In the months leading up to launch, NASA has conducted critical pre-flight tests, including a wet dress rehearsal, a full countdown, and fueling simulation without astronauts on board. During these preparations, engineers encountered issues such as hydrogen leaks and communication dropouts, all of which required troubleshooting. However, the most persistent focus remains on Orion's heat shield, the system that must protect the crew when the spacecraft re-enters Earth's atmosphere at lunar return speeds. To understand why the heat shield has become the focal point of discussion, we first need to understand what Orion will experience during re-entry. When a spacecraft returns from the moon, it travels much faster than a spacecraft coming back from low Earth orbit. Low Earth orbit vehicles, such as the International Space Station crew capsules, re-enter at roughly 17,500 miles per hour. Orion, returning from lunar distance, will hit Earth's atmosphere at close to 25,000 miles per hour. That difference in speed may not sound dramatic at first, but kinetic energy, the energy of motion, increases with the square of velocity. This means that even a modest increase in speed results in a much larger increase in energy that must be dissipated. In practical terms, the thermal and mechanical stress on the spacecraft is significantly greater. What is a heat shield? A heat shield is part of a spacecraft's thermal protection system. Its purpose is to protect the vehicle and crew from extreme heating during atmospheric entry. As Orion descends, it compresses the air in front of it. This compression generates intense heat, not because the air is rubbing against the capsule, but because compressed gases heat up dramatically. Temperatures around the capsule can approach 5,000 degrees Fahrenheit, comparable to half the temperature of the sun's surface. Without protection, the aluminum structure of a crew capsule would melt within seconds. What does ablative material mean? Orion's heat shield uses a material called AvCoat. AvCoat is classified as an ablative material. Ablative means that the material is designed to gradually burn away. As it chars and erodes under high temperature, it carries heat away from the surface. This controlled destruction is intentional. Instead of trying to resist heat indefinitely, the material sacrifices itself in layers, protecting the structure beneath. Avcoat is not new. It was also used during the Apollo missions in the 1960s and 1970s. On the surface, that history sounds reassuring. However, the structure of the shield is not identical. How is Orion's heat shield different from Apollo's? The Apollo capsules used a honeycomb structure. The heat shield contained more than 300,000 small cells, each filled with a blade of material. If one cell failed or degraded unexpectedly, the damage remained localized. The surrounding cells continued functioning independently. Orion uses a different structural approach. Instead of hundreds of thousands of small cells, Orion's shield consists of fewer than 200 large blocks of Avcoat bonded together into a single shield, roughly 16.5 feet in diameter. The material chemistry is proven, but the structural layout, larger segments rather than small cells, changes how stress and heating distribute across the surface. That difference became important during Artemis I. What happened during Artemis I re-entry? Artemis I, flown in 2022, was Orion's first full-scale lunar mission and its first real lunar-speed re-entry. Ground testing and computer simulations had predicted how the shield would behave. After splashdown, however, engineers discovered that large, brick-sized pieces of Avcoat had detached from the heat shield. The loss created deeper cavities than models had anticipated. This was not a catastrophic failure. The spacecraft survived re-entry. A 2024 NASA Inspector General report concluded that the crew likely would have survived had astronauts been on board. But the report also confirmed something important. The shield did not perform exactly as predicted. That difference between expectation and reality is what drives the current discussion. Why does one test matter so much? Re-entry from lunar distance cannot be perfectly replicated on Earth. Wind tunnels and arc jet facilities can simulate portions of heating, but they cannot recreate every variable of real atmospheric entry at full scale. That makes actual flight tests the most reliable form of validation. So far, Orion has completed only one lunar speed re-entry, Artemis I. That single data point showed unanticipated material loss. In engineering terms, unexpected behavior does not automatically mean unsafe. But it does mean models need refinement. And when human lives are involved, margins matter. What did NASA change for Artemis II? Rather than redesigning the heat shield before Artemis II, NASA chose to adjust the spacecraft's re-entry trajectory. A re-entry trajectory describes the path and angle at which a spacecraft enters Earth's atmosphere. Small changes in angle can significantly affect heating duration and peak temperature. For Artemis II, Orion is expected to follow a profile that produces higher peak heating but for a shorter period of time. The goal is to reduce prolonged heating exposure, which may have contributed to material loss during Artemis I, while keeping total thermal load within acceptable limits. In simple terms, instead of spreading heat over a longer period, the spacecraft experiences a sharper but shorter heating pulse. NASA's internal analysis suggests this approach reduces the conditions that led to large Avcoat chunks detaching. What are the concerns? Some critics argue that adjusting trajectory addresses symptoms rather than structure. The underlying design, large Avcoat segments bonded together, remains unchanged for Artemis II. Another point of discussion is that the revised re-entry profile has not yet been validated in a full lunar mission without crew. Artemis II would be the first time this adjusted profile is flown at lunar return speed. In engineering practice, there is always a balance between redesigning hardware and adapting operational procedures. Redesigning a heat shield would likely require extensive testing and could delay the mission by years. Adjusting flight parameters can be implemented faster, but must rely heavily on updated modeling. How significant is the risk? Risk in human spaceflight is never zero. Estimates from independent analysts vary, with some suggesting probabilities of serious heat shield failure ranging from 1 in 5 to 1 in 50. These numbers are debated and depend on modeling assumptions. For comparison, NASA historically aims for loss of crew probabilities significantly lower than 1 in 100 for modern missions. Exact figures for Artemis II have not been publicly finalized. The key point is not the exact number. The key point is that even small uncertainties become central when astronauts are involved. What about the wet dress rehearsal issues? Separate from the heat shield discussion, Artemis II has faced technical issues during its wet dress rehearsal, a full fueling and countdown simulation. A wet dress rehearsal tests cryogenic propellant loading. Cryogenic means extremely cold liquid fuels, such as liquid hydrogen and liquid oxygen, which must be handled under precise conditions. During rehearsal, engineers encountered a hydrogen leak linked to a valve, delays due to cold weather, and temporary communication dropouts. Another issue involved the buildup of gaseous nitrogen in confined areas near the crew module and launch abort system hatches. These issues are not unusual in complex launch systems. The purpose of rehearsals is to identify and resolve such problems before committing to launch. However, they contribute to schedule pressure. Launch windows for lunar missions occur in specific clusters, dictated by orbital mechanics. Why are launch windows so restrictive? Earth orbits the Sun. The Moon orbits Earth. Both rotate on their axes. For Orion to follow a free return trajectory, meaning the Moon's gravity naturally swings the spacecraft back toward Earth, the geometry must align. These alignment windows typically last about a week, followed by gaps of several weeks when conditions are not favorable. Weather adds another constraint. Storms can delay launch attempts. Solar illumination is also critical. Orion's European-built service module relies on large solar arrays for power and cannot remain in extended darkness. All of these variables must align: vehicle readiness, orbital geometry, weather, and recovery conditions in the Pacific Ocean. In summary, Artemis II sits at the intersection of hardware validation, operational adjustments, and precise timing. The heat shield debate is not occurring in isolation. It exists within a broader system of technical and scheduling constraints. Artemis II is not just another test flight. It is the first time NASA will place astronauts on top of the Space Launch System and send them beyond low Earth orbit. That alone gives the mission strategic weight, but its importance goes further. If Artemis II is successful, it will validate the integrated performance of three major systems working together: the Space Launch System rocket, the Orion crew vehicle, and the ground and recovery infrastructure that supports them. Each of these elements has been tested individually. Artemis II is the first time they operate together in a crewed deep space environment. That validation is essential for Artemis III, the mission intended to land astronauts on the lunar surface. If Artemis II demonstrates that Orion's heat shield performs within acceptable limits under crewed conditions, NASA can proceed toward a lunar landing with higher confidence. If unexpected issues arise, Artemis III would likely face delay, redesign, or additional uncrewed testing. This is why the heat shield discussion carries strategic implications. The Artemis program is structured in phases. Artemis I tested the system without crew. Artemis II tests it with crew in lunar orbit. Artemis III is intended to execute a landing in partnership with a separate lunar lander system. Each mission builds on the previous one. If Artemis II reveals unresolved thermal protection concerns, the timeline for Artemis III could shift. Lunar landing schedules depend not only on lander readiness, but also on Orion's ability to safely return astronauts to Earth. Beyond mission sequencing, Artemis also carries geopolitical and policy weight. The United States has publicly stated its intention to establish a sustained human presence on the moon. That includes long-term surface operations and potentially infrastructure such as habitats, power systems, and logistics networks. Other nations are also pursuing lunar missions, including China's expanding lunar exploration program. In that context, Artemis II represents more than a technical milestone. It signals whether the current U.S. deep space architecture is mature enough to support sustained exploration. If Artemis II proceeds smoothly, it strengthens confidence in NASA's chosen hardware approach. If challenges emerge, it may trigger broader reassessment of timelines, funding allocations, or hardware design strategies. There is also the matter of public trust. Human spaceflight programs operate under intense scrutiny. Historical accidents, such as the loss of Space Shuttle Columbia in 2003, reshaped NASA's safety culture and engineering review processes. In both Columbia and earlier incidents, the technical failures were linked to thermal protection systems and risk assessment decisions. Because of that history, any discussion involving heat shields naturally carries weight. NASA leadership has stated that Artemis II will not launch unless defined safety thresholds are met. At the same time, it has acknowledged that Artemis III will incorporate modifications to the heat shield design. If improvements are planned for future missions, observers may reasonably ask whether those improvements should be implemented earlier. The counter-argument is schedule impact. Redesigning a heat shield involves manufacturing changes, structural qualification testing, and potentially additional uncrewed flight validation. In a program already years behind its original schedule, every redesign has consequences. This creates a classic engineering trade-off. Implement hardware redesign now and accept delay, or proceed with validated mitigations and refine hardware in parallel for future flights. The decision does not occur in isolation. Artemis is part of a broader effort that includes commercial partnerships for lunar landers, habitat systems, and surface infrastructure. For example, companies such as Voyager Technologies and Max Space are exploring expandable habitat technologies aligned with long-term lunar outpost goals. Those future plans assume that crew transportation between Earth and lunar orbit is reliable. If Artemis II successfully demonstrates crewed lunar return capability, it reinforces the foundation for these commercial and governmental initiatives. If not, downstream projects may need to adjust. In other words, Artemis II is not only about surviving re-entry. It is about validating the transportation backbone for sustained lunar operations. If the heat shield performs within expected parameters under the revised re-entry profile, it would suggest that operational adjustments can effectively manage the identified risks. If discrepancies appear again, NASA would likely face increased pressure to implement structural redesign before Artemis III. Either outcome would shape the next phase of human lunar exploration. As of now, several variables remain open. First, the revised re-entry trajectory for Artemis II has not yet been validated in a real lunar speed return with astronauts on board. NASA's updated modeling suggests that shorter duration peak heating should reduce the type of material loss observed during Artemis I. However, real atmospheric re-entry is the definitive test. Until Artemis II completes that phase successfully, the performance of the heat shield under the new profile remains partly theoretical. Second, pre-launch testing is still ongoing. Wet dress rehearsal issues, such as hydrogen leaks, communication dropouts, and environmental control concerns are being addressed, but final clearance depends on the formal flight readiness review. That review determines whether the integrated vehicle, ground systems, and operational teams meet launch criteria. Third, launch timing itself is dynamic. Orbital alignment between Earth and the Moon creates specific windows for a free return trajectory. Weather conditions and recovery, zone readiness in the Pacific Ocean add further constraints. If technical adjustments require additional testing time, the launch may shift to a later window. Beyond Artemis II, NASA has indicated that Artemis III will incorporate updates to the heat shield design. The details and testing timeline for those modifications will be closely watched. If Artemis II confirms that the revised re-entry approach performs as expected, Artemis III may proceed under current plans. If not, redesign and additional validation could become necessary before attempting a lunar landing. What makes this moment significant is not certainty, but sequence. Artemis II is positioned between uncrewed testing and lunar surface return. It is both a demonstration and a decision point. In the coming months, attention will focus on final system verification, confirmation of launch dates, and eventually, real re-entry data from a crewed mission. As those milestones approach, the broader question will remain: has every critical system been validated to the level required for sustained human exploration beyond Earth orbit? We will continue following the technical updates and mission developments as they unfold, because the answers will define the next phase of the Artemis program.